Hi, I am Rowdy the Roadrunner. Welcome to the Computational Turbulence and Visualization Lab. The CTV Lab is part of the Department of Mechanical, Aerospace, and Industrial Engineering at the University of Texas at San Antonio. Our mission is to promote numerical thermal fluid research for aerospace applications by means of state-of-the-art high-performance computing, artificial intelligence, machine learning, and scientific visualization technology for undergraduate and graduate students, faculty, and UTSA collaborators. On our left is a computer simulation of air flowing over curved surfaces at nearly 3 times the speed of sound. The colors reveal the invisible, how air moves, compresses, expands, and forms swirling motion. As air moves over the first curve, it can rapidly compress and create a shock wave similar to those around supersonic aircraft. In some regions, the flow becomes chaotic, forming turbulent swirling structures. Interestingly, the surface shape can also stabilize the airflow. Engineers study these effects to design faster, safer, and more efficient aircraft and spacecraft. Simulations like this allow us to explore extreme flight conditions that are difficult to recreate in real life. On the right, the computer divides the space into about 10 million small pieces to accurately simulate how air moves. A crossflow jet occurs when a jet of air or gas enters an airflow moving in another direction. It is common in aerospace systems like jet engines, rocket thrusters, and fuel injection, where precise mixing and airflow control are essential. To study these flows, scientists use computer simulations that track tiny virtual particles acting as tracers to visualize airflow and mixing. Our team developed a GPU-accelerated program to track particles more efficiently. In a large-scale test, we simulated 20 billion particles in a high-resolution airflow model using 4 GPUs. In this visualization, 380 million particles injected into the sonic jet show how a high-speed jet interacts with a crossflow. Early scientists used smoke and dye to visualize airflow and study turbulence, since air is invisible. The idea was simple. Seeing it makes it easier to understand. In the past decade, virtual reality, VR, and augmented reality, AR, have transformed data visualization. VR creates a fully digital environment to explore, while AR overlays digital information onto the real world, helping us understand invisible phenomena like airflow. On the left, a user explores supersonic airflow over curved surfaces using virtual reality. On the right, the same simulation appears in augmented reality, with digital flow patterns layered onto the real world. And that's what our lab is all about, turning invisible physics into insights that shape the future of flight. Our vision is to become a top-notch laboratory in the areas of high-fidelity, computational fluid dynamics, and virtual and augmented reality in Texas and the nation. Thank you for watching and learning more about our lab. We appreciate your time, and we look forward to sharing more of our work with you. Goodbye.